The interesting thing is that Andy is no longer here. Andrew Appel has been going exactly the other way. He's been trying to lower the semantic level of the thing that the axioms in the proof, which makes the proof even bigger, but it makes the axiom set smaller and easier to manually prove correct. So it's a slightly different approach. So let me give you a motivating example, and I guess I won't get to my final things. So, for example, you want to have a virtual machine that supports dynamic typing with an unbounded number of user-level types, which is, for example, what Java does. But obviously, for an efficient implementation, we don't want unlimited number of types down at the bottom level virtual machine. So, and you can actually use proof-carrying code to establish type safety, but the proofs are very complex. And so, what our virtual machine does, it actually has a user-defined, a user-level field called tag pointer, or the user-level tag field. But the virtual machine guarantees that this user-level tag field can only be read by two special instructions, tag read and tag write. And we guarantee that property by the construction of the virtual machine. Now, if you want to prove that the type of something hasn't changed, now all you have to do is have to show that a certain sequence of instruction doesn't include the tag write instruction, because there's no other way of changing the type, the dynamic type of an object, which is much simpler than if you were trying to do proof carrying code for binary code with huge amounts, where you actually have just memory instructions that you read and write. Now, so we're actually splitting the burden, or the burden of proof even, in this case, between a construction of a higher level VM than we currently have, and a proof type PCC system. Okay, so, and then I'm going to just very quickly just mention this. So the verification problem, we've had self-certifying code, which was the original idea of Java. You actually, rather than having a certificate, you look at the code itself. The next step was proof-carrying code, which was rather than performing a complete data flow analysis, you actually only show that a certain program is a legal program by looking at a proof. And what we've been doing at Irvine, and we actually even have a patent on now, is to come up with code formats, so transportation formats that are inherently safe. So what you're basically doing, you're coming up with communication languages in which you cannot even express an illegal program to begin with. And the interesting thing is that you can do that not only to express legal programs that don't require any verification, but actually even to encode in a tamper-proof manner information that an optimizer and compiler can use to do base optimization decisions. So I guess okay. I'm only going to give you very short idea of how this works. So this is just, if you have a sample Java program, and you have these possible assignments that can be written in Java, what the Java type checker needs to do, or the Java verifier needs to do, is to make sure that these illegal assignments don't occur. And it needs to do that via a complex way of tracking, because it could be done via the stack, such an illegal assignment. Now, the idea is, of course, very simple. What you do is you enumerate all the legal assignments, and rather than actually communicating what actually happens, you only transmit the index of the assignment that you mean. And now the engineering thing that I can't get into today is, how do you find ways of enumerating all the legal programs in such a way that you can do this very efficiently, as an online process while you're transmitting the stuff. And the interesting thing is that these encodings are actually more compact than the best general purpose data compression algorithm applied to either Java source or Java object code. Because what you're actually doing is you're putting, squeezing entropy out of the system. Our system only includes the legal Java programs, which are a smaller set than all the legal source, all the things you can write in ASCII, or all the Java bytecode streams, which might include illegal programs as well. So it's quite natural that such an encoding would be denser. So you get incredibly dense encodings that are provably safe by construction rather than requiring verification after the fact. And anyone who's interested, can come and talk to me later. I think I'm just going to stop right there. Yes?
So one of the more expensive things to do on an optimizing compiler is register allocation.
Yes.
Is there some convenient way you can propose a possible register allocation in this format?
Well, it's easy if you can only do it as far as you completely separate the types of the different. You obviously want type safety, so you would have to do it, by separating types. We have one format that we had a paper in PLDI 3 years ago, where we're actually transporting a safe variant of SSA across the wire. So you basically get SSA at the target machine, and there's actually going to be a tech report which is currently I'm editing right now, which we're going to be submitting to CGO, which shows we integrated this into Jalapeno or JAX RVM completely. We actually share the low-level code generator with the existing JAX RVM, but the incoming class files are not Java. So we can actually mix and match between Java class files and our own intermediate representation completely. And rather than first having to lift the bytecode to SSA and then compiling it back down, we actually have basically trivial verification, which is just a well-formedness property of the format itself. And then you transpose directly into JAX RVM SSA, internal SSA representation. And that's a sideways translation rather than having to do lots of lifting. Yes?
I just want to follow up because I didn't intend my question to sound as negative as it did. My point was, I think that this is tremendously useful, but not so much for building untrusted operating systems, but for improving the reliability of a trusted operating system. If you could do a trusted operating system, I mean, if you do a regular operating system on top of this kind of framework, you'd probably greatly improving the reliability of just the basic programming of that system. So it seems to me that motivation is very sound.
Doesn't it bother you that we distinguish trusted operating systems from operating systems?
Well, I didn't mean to say by trusted I mean regular. We trust operating systems today, and if you were kind of arguers for not trusting the operating system, that seems.
I guess I won't be able to get to that. Okay. I'll just stop here. I mean, I've got a lot more to say. If you're really interested, come and talk to me or invite me to give a talk somewhere. Thanks.
Thank you, speaker.